Okay. We're going to look at orbital diagrams, okay? At this point, you should have watched the entire video on electron configurations. You should understand it. You got it. Everything I said, you should understand, or you should have already asked about and gotten clarification. Now we're going to just do kind of the same thing, but it's going to be in terms of orbital diagrams. It's just kind of a different way to look at electron configurations. So let's try to keep it simple here. And let's get our pen. I want green, let's do blue. We've got orbital diagrams, okay? And what we're going to do is we're going to use boxes to represent orbitals, and we're going to use arrows or arrows as such, however, are going to represent the electrons. Okay? And what happens if I go like this? All right, so let's bring back chlorine. All right. Chlorine we wrote earlier as 1s2, 2s2, 2p6, 3s2. All right, that's ugly. All right, let's turn that into an orbital diagram. All right. Oops, hold on, we got to put a 3p5 right there. That's chlorine. Oh, that's what. Okay. So we're going to go 1s, and s has one orbital, so we'll get one box. And we will do arrow up, arrow down. Okay, the arrows must go in opposite directions because electrons in the same orbital have opposite spins, okay? So you must represent those electrons with one arrow going up and one arrow going down to demonstrate the opposite spins of them, of the two electrons in the same orbital. We've got a 2s. S only has one orbital, and one electron will be spinning up while the other is spinning down. And with 2p, a p has three orbitals, so we will demonstrate that with three boxes. You may see these actually labeled, right? Like the T2px orbital, 2py orbital, 2pz orbital. Don't worry about it. The little subscripts are just representing, right? You could see this is 2px, 2py, 2pz, whatever those little subscripts are. You don't need to memorize them. They're just referencing individual orbitals, okay? You'll see that on one of your worksheet. Now, these three 2p orbitals, you need to understand, and this is new information for those of you that had me last year, these are equal energy orbitals, all right? They're also called degenerate orbitals, or basically degenerate orbitals are equal energy orbitals. They are equal in energy because they are all on the same energy level and they are all the same type of orbital. They are not equal in energy to the s orbital that's also on the second energy level. They are actually a little bit further from the nucleus, just a little bit. So they are not equal in energy. And equal energy orbitals, degenerate orbitals, when they get electrons, each equal energy orbital gets one electron before the other before any equal energy orbital gets to. I'm actually going to write that down. It's a rule. There is a name for it. It's either Hund's rule or the Pauli exclusion principle. I think it's the Pauli exclusion principle. I may be wrong though, but each equal energy orbital, and here we have three, each equal energy orbital gets one electron before any equal energy orbital gets 2. Okay, so that's why it's always arrow up, arrow up, arrow up, and then we will go arrow down, arrow down, arrow down. Okay, it's got to be done in that order. After 2p comes 3s, there is 1 orbital, and we've got 2 electrons spinning oppositely in that 1 orbital. 3p gets 3 orbitals, right? There are 3 orbitals on that p subshell. We can call them x, y, z. 3px, 3py, 3pz. They are degenerate orbitals. They have the same equal amounts of energy. So we're going to have to apply this rule where each equal energy orbital gets 1 electron before any gets 2. So what we see here is our electron or orbital diagram for chlorine, right? That's what's going on right here. And that orbital diagram shows that chlorine has 1 half-filled orbital. We could attribute that to the charge on a chloride ion, which we know to be -1, because when this chlorine atom gains an electron, he would like to have 1 in order to have that magic stable octet of 8, right? This is his valence shell here. And as an ion, he in fact gains an extra electron to fill up that outer orbital that is only half full when it is an atom. So that's why we would see that the ion would be more stable than the atom. Okay. It's important to realize that you can identify based off the periodic table who's going to have 3 half-filled orbitals. That would be nitrogen here. Right? He's got 3 half-filled orbitals because we know he ends in 3p3. So you need to visualize that in your head as 1, 2, 3, right? Those are my arrows, guys. So I see that there's actually 3 half-filled orbitals. Oxygen, who ends in 3p4, right, would have that extra. He would have the, that is just horrible, horrible, horrible. Oxygen would have the 2 half-filled orbitals, which would explain why oxygen gains the -2 charge, right? Nitrogen, once again, if I could get rid of him, nitrogen had the 3 half-filled orbitals, which he would want to gain 3 electrons to complete his outer shell, giving him the 3 negative charge. Chloride, which only has the 1 half-filled orbital, right? Naturally, chloride is 3p5, and he's got the 1 half-filled orbital, which would explain why he forms the -1 ion, right? So I hope all that makes sense to you. If it doesn't, you definitely need to ask, and I can be happy to go over it with you more. So the periodic table is so much more than just atomic numbers and atomic masses and symbols. It tells us, remember, it tells us the location of our valence electrons. It tells us how many valence electrons we have. And we can even kind of figure out how many completely filled orbitals we have, half-full orbitals, totally empty orbitals, right? Boron here has 2 empty orbitals. Carbon has 1 empty orbital. Nitrogen doesn't have any empty orbitals, but has 3 half-filled orbitals. So you need to be comfortable with that. Another thing I want to make sure you realize, now might be the time to do it, is let's do, whoa, that's like a perfect line. Let's look at manganese here, atomic number 25, and let's write the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 3d5. I want to make sure that you realize that this is his highest energy level, as is the case with any transition metal. It will be the case that this energy level over here is his valence shell. It's not the 3D, it's the 4S. Oops, it's not the 4D, it's the 5S, etc. So that he's got the 2 valence electrons. Okay. Ew, why won't it let me write? I wonder. It's got 2 valence. Okay, let's see, 2 valence. And when he participates in bonding or forms ions, it is in fact these electrons that are lost, and it is not these, right? These are the electrons lost. These electrons are lost when forming ions. I'm telling you, you're going to see questions about that, and most of you guys are going to miss it. That's in my experience. That's the way this is going to go down. As an ion, he would first lose one of those and one would be remaining. And then if he formed a 2+ ion, he would then lose both of those. Apologize for that. He would then lose both of those. They would be gone. And then these would be removed. But these are further from the nucleus, so they're going to be removed first. All right, you need to make sure you realize that. Other than that, I'm going to stop with orbital diagrams. Okay, so let's stop share and end. See you guys later.